All right, today we're going to finish up chapter 2 on water. You guys will be responsible for this material, and we will have a quiz on this on Friday on this material and all the rest of chapter 2. Last lecture on last Friday, we left off with this problem here where we solved for the concentration of protons in the total volume of 250 milliliters. We took the negative log of that proton concentration to solve for pH. After lecture, one of your classmates came up and asked if we could use the simple C1, oops, let me get the pen going. C1V1 equals C2V2 for this problem. And you absolutely can, where you can, for C1, put 1 millimolar, or convert that to mole, but we can do 1 millimolar. V1 would be 50 milliliters. C2 would be X, and V2 would be 250 milliliters. Now, because we're on the milli scale for both the volume and the concentrations, you really don't need to convert to moles and molar and liter, but you should. Again, if you can't recognize that those milli units cancel out, then go ahead and just convert to molar and to liters. All right, when we solve for X, we should get 2 times 10 to the negative 4 molar proton and work through that. And we can then just put that into our pH equation in order to get the pH equal to 3.7. So you can use either approach 1 or approach 2. All right. So this is when we have a strong acid or a strong base. We can calculate either the pH or the pOH. All right. So let's talk about when we have a weak acid or base. And a weak acid or base is when our molecule only partially dissociates into hydrogen ions and water. And so weak acids are normally denoted as HA, where we have a weak acid that's associated and yields a proton and a weak base, sometimes referred to as the conjugate base. Okay, so what's the equilibrium expression for a weak acid? This is referred to as Ka. And again, it's going to equal the concentrations of products over the concentration of the conjugate base over the concentration of the weak acid. All right, and we need to know this expression, so we're going to put that in a blue box because that's important to know. Okay, so we can determine how strong of an acid how close to a strong acid our weak acid is based on the numerical value of a Ka. So a high Ka means that the acid is going to dissociate more and look more like the products, so it's going to be a stronger acid. All right. A low Ka means that your acid is going to be less dissociated and look more like the protonated form, and so it's going to be a weaker acid. Okay, but we can relate our Ka to another term known as pKa. So pKa, just like pH, is equal to the negative log of the Ka. And this is often how we look and talk about our acids in terms of their pKa. Okay, so make sure you know how to determine a pKa from your Ka. So if we have a high Ka and we have a strong acid, that means we have a very low pKa. Likewise, if we have a low Ka and a weaker acid, that means we have a high pKa. So this is essential to understand how Kas and pKas relate to the strength of your acid. Okay? So the Ka, like it says here, is the ionization constant or the acid dissociation constant. And the Ka and the pKa is a measure of how strong your acid is. So you have to be able to determine whether your acid is going to favor the products more readily and look more like a stronger acid, or favor the reactants and look more like a weaker acid or more like the protonated stage, based on the values of a pKa and a Ka. All right, this is essential. So let's relate these to our titration curves. And so all of you have done titrations in Intro Chemistry Lab 2, so in 1120, and you all did acid-base titrations, if I remember correctly. So usually what you have is you have some sort of, I'll just draw it over here, you have some weak acid in a beaker, then you have your burette here, and your burette's filled with some strong base, usually NaOH. All right? And what you do is you actually titrate your base into your weak acid, and you have some sort of either pH meter or indicator that'll change colors to show when the amount of weak acid equals its conjugate base. Okay? That's the whole purpose of a titration. So we can determine the numerical value of our pKa by undergoing a titration. And that's essentially what this figure in your textbook, figure 2-17, is showing us. So what we're doing is we're adding in our equivalents of our strong base, sodium hydroxide, and at some point we have a protonated form, right, in our beaker. We're starting off with our fully protonated, this is acetic acid. As we titrate, we're adding in and we're starting to change the acidity of our solution. At a certain point, at the midpoint, we are then going to have the pH of our solution equal to the pKa. This is extremely, extremely important. So at the midpoint of our titration curve, shown here, the pH is equal to the pKa, which means the amount of weak acid is equal to the conjugate base. That's shown here. The acetic acid, the weak acid, is equal to the concentration of the conjugate base, which is the acetate ion. All right, this is going to be important later because this is known as our buffering region. All right, we'll talk about that in a few minutes. If we continue to add base here, our pH will eventually increase and we'll be left with fully conjugated base, and the equilibrium will be shifted all the way to the products. All right, so this is extremely important to know. It's important to know because it's going to play a role in this buffering against pH changes in biological systems. So this understanding of titration curves is important to understanding biological buffers. All right, so we've only talked about biological processes occurring at a pH of 7, but not all biological enzymes. We're going to talk about enzymatic enzymes in chapter 11, I believe. But not all enzymes do have optimum activity at pH 7. The majority of enzymes do, but for instance, digestive enzymes, pepsin, they have high biological activity, so they're able to undergo their chemistry under extremely low pHs, under acidic condition like that present in your stomach. We also have alkaline phosphatase, which is extremely active in alkaline or basic pHs, and so it's extremely important to understand pH dependency and how biological activity changes with pH. All right, so we can undergo consistency in most of our enzymatic reactions. We said that the majority of reactions have optimum activity or reactivity at pH equal to 7.4. All right. How does this happen? It happens because of the presence of biological buffers. And we'll talk a little bit more about biological buffers in terms of hemoglobin and the transmission of bicarbonate through our blood when we talk about structure and function in chapter 5, and then in 2 chapters from now. All right, but biological buffers are everywhere in our system. We're going to talk about acetic acid, but that's really just a chemical buffer, not a whole lot of acetic acid in our body, but that can just be transferred to citrate buffers and tris buffers and other biological buffers that are present in our body. All right, but what is a buffer? A buffer is any weak acid and its conjugate base. All right, so I said up here that acetic acid is a buffer. It has a weak acid and a conjugate base. Its conjugate base is its ion, its acetate ion. All right, buffers are important because they resist changes in pH with the addition of small amounts of strong acid or strong base. All right, so when we add protons or hydroxide ions, we can resist changes in pH because of this property of buffering capacity. We'll find that buffers usually have a suitable range within plus or minus 1 pH unit of its pKa. And that's essentially what this titration curve in figure 2-17 is showing, that the pKa is 4.76, and that acetic acid can really be used to buffer a solution in the range of 3.76 and 5.76. All right, so how can we relate pH to pKa? Well, we can relate it using our equation, the Henderson-Hasselbalch equation. This is how we can relate pH to the concentration of the acid and the conjugate base in solution. So if you remember it, and if you don't, you need to, pH is equal to the pKa of the solution plus the log of the concentration of the conjugate base over the concentration of the weak acid. Right? A minus is the conjugate base, HA is the weak acid. All right, so let's put that in a blue box, because this is, again, is a formula that you need to know. You should already know this, but make sure you refresh your memory. Okay, so we just said that at the midpoint of the titration curve is where our buffering capacity is greatest. That means that the concentration of the weak acid is equal to the conjugate base, and this just is deriving that. If we have if the ratio of the weak acid and the conjugate base are equal, that means that the log will be equal to 1. The log of 1 is equal to 0. That means that the pH will equal the pKa. So that formula down there is just showing that at equilibrium, at the midpoint, pH is equal to the pKa, because the concentrations of the weak acid and conjugate base are equal. All right, so let's do a couple of questions. These would have been clicker questions, but let's just work through them, and then we'll be finished with this chapter. All right, so given the following titration plot, we have an acid-base ratio, or this could be equivalence of OH, concentration of OH added, and we have the pH of the buffer. So given this titration plot, what is the best buffer capacity of the provided weak acid? Remember, the buffering region is the midpoint, and it's where the change in concentration is minimal. So the flattest part of the titration curve. Flattest, wow, that's bad, part of titration curve. That's where the buffering is greatest, and that says flattest. F-L-A-T-E-S-T. All right. So at a pH of 5.5, what form are we mostly in? We're not in, remember, the buffering is when the concentration of HA is equal to the concentration of A minus. So at a pH of 5.5, we really have all HA. So we're predominantly HA. So it's not that. At 6.5 here, we're getting better, but we're still predominantly HA. Well, let's talk about 8.5 and 9.5 up here. So at 9.5, you should be able to realize that we're mostly in the conjugate base form at 9.5 and 8.5. So only at a pH of around 7.5 is this relationship true, and are we at our best buffer capacity of this weak acid. All right, let's do a more numerical problem where we have the pH of a solution containing 10 mils of 0.5 molar acetic acid and 5 mils of 2 molar acetic acid, sodium acetate. We want to determine what the pH of that solution is. So the first thing you need to do is determine what formula you're looking for. You have some concentrations and you have a pKa. So you should be, and you're trying to determine pH. So you should be able to determine that we want to use that Henderson-Hasselbalch equation. All right. First thing, if you don't know how to do anything else, write the formula that you need to use on your test or quiz. You'll get at least a point or two for setting it up properly. Now we need to identify the concentrations of A- and HA. So let's determine HA first. So the concentration of HA, the first thing we need to do is determine the number of moles of weak acid, and we can do that either by M1V1 equals M2V2 or by solving for the number of moles of acetic acid. So I'm going to do that. We've got 0.5 moles of acetic acid per liter. And we want X moles equal 0.010 liters. And that should give me, by multiplying those two together, 5 times 10 to the negative 3 moles of HA. All right, we divide that by the total volume, which is just 1 liter, and so our final molarity of HA, or concentration, is going to be 5 times 10 to the negative 3 molar. All right, what about the concentration of A minus? Well, based on our solubility rules, we should know that sodium acetate will completely dissociate into sodium molecules and acetate molecules, or ions, sorry. And so we know complete dissociation, that the concentration of sodium acetate will equal the concentration of acetate ion, which is our conjugate base. So we'll solve the same way. So 2 moles per liter of acetate equals X moles times 0.123 liters. And I should get 0.01 moles of acetate. And if I divide by the total volume of 1 liter, I get 0.01 molar of acetate. Well, now I have all my components. I'm solving for pH. So that's 1, 2, step 3. My pKa is 4.76 plus the log. Make sure you put the correct value on top. So the numerator is our acetate ion. So because it's a 1 liter solution, it's 0.01 molar acetate divided by our weak acid, which is acetic acid, 5 times 10 to the negative 3 molar. And I don't have the math worked out in front of me, but I got a pH equal to 5.06 when I solved for that. So you would just divide the conjugate base by the conjugate acid, take the log, and add that value to 4.76. All right. All right, so on your homework, there's some questions and also on previous exams where there was a question about choosing the best biological buffer. So this is extremely important that when you're making a buffer in the laboratory or in the body, that you select the right biological buffer. All right, so we have this biological table with values of our Ka values and our pKa's. Remember that a low pKa equals stronger acid. Hopefully you can see that. It might be cut off, but equals a stronger acid, all right? And a higher Ka equals a stronger acid. Okay, so when we're looking for a better biological buffer, we want the buffer that resists changes around that pH unit. And remember, that occurs when the pKa equals the pH is the best biological buffer. And we said that the best biological buffer is plus or minus 1 pH unit away from the pKa. Okay, so we want to have a biological buffer at pH 8. We look in our table and we see that succinate has a pKa value of, sorry, that's the second one, pKa 2, so it's diprotic. So we'll just look at the succinic acid, has a pKa equal to 4.21, and phosphoric acid has a pKa 1 or pKa 2 of 6.82. Okay, and I would tell you what protonated state to look at. So when we look at our value of which one has a pKa value closer to 5, we would say that 4.21 is plus or minus 1 pH unit away from the pKa, which is 4.21. All right, what about ammonia? Would ammonia or piperidine be a better biological buffer at pH 9? Well, we look at the table and we look and see that ammonia has a pKa of 9.25 and piperidine or pipes has a pKa value of 11.12. And so we would be able to say that ammonia is a better biological buffer at pH 9 because its pKa is closer to the pH of the solution that we desire. Okay, and there are some questions on this on either the old test or the old quizzes and homework, sapling homework as well. Okay, so with that, we are done with chapter 2. Make sure you understand hydrogen bonding and identifying donor and acceptor. Understand the terms hydrophilic, phobic, and amphiphilic, intermolecular forces. Understand and review all the intro chem in terms of strong acids and bases, pHs, weak acids and bases in regards to Kas, pKas, and those titration curves. Be able to identify the species on a titration curve. And then understand how these weak acids and bases relate to the Henderson-Hasselbalch equation and biological buffers. Okay, again, we'll have a quiz on this on chapter 2 on Friday, February 3rd. On Wednesday, we'll begin chapter 3. I encourage you, if you have questions on this material, to either come to my office hours or to attend Lee tutoring either tonight or on Wednesday with Emily. Okay, thank you. Have a good day.